This is chapter number 4 describing variability from the statistics book by Robert S. Witte and John S. Witte. First of all, it talks about the intuitive approach. What it says is that you probably already possess an intuitive feel for differences in variability. It gives us a figure in which it considers three distributions. As we can see in the distribution A, all the values, there are 7 values in the distribution and all of them equal 10. In other words, this distribution is not at all varied. All the distributions equal a particular value, which is the mean. Now coming to distribution B, there are 5 values which equal 10. There is one which is equaling 9 and there is one which equals 11. So in a sense, there are 5 values which equal the mean. There is one which is 1 less than the mean and there is another which is 1 greater than the mean. Although the mean is the same as in the first case, which is 10, but this distribution is a bit more varied than distribution A. Coming to distribution C, what we see is that there is one value which equals 10, there are two which equal 9, there are two which equal 11, and there are two which equal 7 and 13. So in a sense, this group is the most varied. What it asks us to do is that before reading on, rank the three distributions from least to most variable. Your intuition was correct if you concluded that distribution A has the least variability, distribution B has intermediate variability, and distribution C has the most variability. This is what we saw, where distribution A is the most tightly packed, so to say, around the mean. Distribution B is intermediately tightly packed around the mean, and distribution C is the least tightly packed around the mean among the three of the observations. Now, what is the importance of variability? Variability assumes a key role in an analysis of research results. For example, a researcher might ask, does fitness training improve, on average, the scores of depressed patients on a mental wellness test? To answer this question, depressed patients are randomly assigned to two groups, fitness training is given to one group, and wellness scores are obtained for both groups. So, what are we trying to do here? We are trying to understand whether fitness training improves, on average, the scores of depressed patients in a mental wellness test. So, there is a mental wellness test, and we want to understand whether a fitness training can improve the scores of depressed patients. Now, to answer this question, what we have done is we have distributed the depressed patients into two groups, and this distribution is done randomly so that there is no bias towards any patient. And these two groups are called the control group and the treatment group. The patients in the control group are not given the treatment, and the patients in the treatment group are given the treatment. Now, after the fitness training is given to one group, which is the treatment group, wellness scores are obtained for both the groups. So, what we assume here is that before the experiment was done, the wellness scores for both the groups should be almost similar. Because we have randomly distributed the patients into two groups, so whatever dissimilarities might have been there should have been cancelled out. And after we have given the fitness training, we are trying to measure the scores for both the groups. Now, what it says is that let's assume that the mean wellness score is larger for the group with fitness training. Is the observed mean difference between the two groups real or merely transitory? This decision depends not only on the size of the mean difference between the two groups, but also on the inevitable variabilities of individual scores within each group. To illustrate the importance of variability, Figure 4.2 shows the outcomes for two fictitious experiments, each with the same mean difference of 2. So, what it shows is that there are two experiments in which it shows the outcomes of two fictitious experiments which have the same mean difference of 2 before and after the experiment, but with the two groups in experiment B having less variability than the two groups in experiment C. Now let's see what figure 4.2 shows. So this is the figure 4.2 where this is experiment B, where the shaded portion is the mean wellness score before the experiment, and the unshaded portion is the mean wellness score after the experiment. Or B is the shaded portion is the mean wellness score of the patients who are not given the treatment, that is, who are in the control group, and the unshaded portion is the distribution of mean wellness scores for the patients who have been given the treatment. Now, the mean for the patients who have not been given the treatment, which is symbolized by x bar b, is 10, as we saw in this distribution. This is the distribution with which we are working right now. The mean was 10. Now, there is experiment C, which is conducted over the group C. The shaded portion are the scores of the control group, and the unshaded portions are the scores of the treatment group. As we can observe from these figures, is that the difference is more pronounced in experiment B than in experiment C. In experiment C, what we observe is that there is a large amount of overlap between the scores of the control group and the treatment group. Although the mean difference in scores are the same, that is, the mean scores have increased from 10 to 12 for both the groups, but in experiment C, what we find is that, say for example, for the score 11, there are two patients who belong from the control group who score 11, and there are two patients who belong from the treatment group who score 11. So there is a large amount of overlap in experiment number C. That is what we can see intuitively. Notice that groups B and C in figure 4.2 are the same as their counterparts in figure 4.1. Although the new group B star retains exactly the same variability as the group B, each of its 7 scores and its mean have been shifted 2 units to the right. Likewise, although the group C star retains exactly the same or the most variability within the groups, each of its 7 scores and its mean have been shifted 2 units to the right. Consequently, the crucial mean difference of 2 is same for both the experiments. Okay. Now, variabilities within groups assume a key role in inferential statistics. What are we trying to do in inferential statistics? In inferential statistics, we have a sample from which we try to measure and assume infer, so to say, the population parameters. That is why it is called inferential statistics. Briefly, the relatively smaller variabilities within groups in experiment B translate into more statistical stability for the observed mean difference of 2 when it is viewed as just one outcome among many possible outcomes for repeat experiments. Now, this distribution is just one among many possible distributions from the group B. It might as well happen that once we do the experiment again, we will not get the same mean and the same distribution. The distribution will remain more or less the same, but will not get the same mean. The mean will fluctuate. Maybe it will be 9, maybe it will be 11. So, but since this distribution is fairly tightly packed around the mean, we can say that it has more statistical stability for the observed mean difference of 2. Now, when we see the group C, it is much more varied. So, it might as well happen that the next time we are picking up a sample from this population, we will get the distribution which is of the unhighlighted portion or which has the mean of 12. It is much more likely in this case, whereas it is much less likely in this case, in experiment B. So what it says is that, therefore, insofar as similar but not necessarily identical mean differences would reappear in repeat experiments, so in repeat experiments we would find similar, it will not be same, but similar mean differences in future experiments as well. From that we can conclude that the observed mean difference of 2 in experiment B probably reflects a real difference in favor of the treatment. On the other hand, the relatively larger variabilities within groups in experiment C, we will now move ahead to discuss a few metrics of measuring variability. Exact measures of variability not only aid communication but also are essential tools in statistics. One such measure is the range. The range is the difference between the largest and smallest scores. So, for example, in distribution A, which is the least variable, the range is essentially 0 because the smallest value in the distribution is 10 and the largest value in the distribution is also 10. So the range is 0. For the distribution B, the smallest value is 9 and the largest value is 11, giving us a range of 11 minus 9 equal to 2, which signifies that it is a bit more varied than distribution A. For distribution C, the smallest value is 7 and the largest value is 13, which gives us a range of 13 minus 7 is equal to 6, which signifies that this is the most varied distribution among the three. That is what it describes next. Distribution A, the least variable, has the smallest range of 0. Distribution B, the moderately variable, has an intermediate range of 2. And distribution C, the most variable, has the largest range of 6, which is in agreement with our intuitive judgments about differences in variability. The range is a handy measure of variability that can be easily measured and understood. But it has a few shortcomings. First, since its value depends only on two scores, the largest and the smallest, it fails to use the information provided by the remaining scores. Now, since for calculating range, we are bothered only with two scores, the largest and the smallest, and we ignore all the intermediate scores, we are not using the complete information provided by the whole distribution. Furthermore, the value of the range tends to increase with increases in the total number of scores. How come? Say the range of adult heights might be 6 or 8 inches for half a dozen people, whereas it might be 14 or 16 inches for 6 dozen people. Now, as we increase the sample size, there is a greater likelihood that we will encounter outliers. People who are shorter than the general population and people who are taller than the general population. So once we do that, the range will automatically increase as the range is the difference between the smallest and the largest value. Larger groups are more likely to include very short or very tall people who, of course, inflate the value of the range. Instead of being a relatively stable measure of variability, the size of the range tends to vary with the size of the group. This signifies that although range is a very range is an range is very easy to calculate, it is not very stable. It changes. It tends to change with the change in the sample size. Coming to the next metric of measuring variability, the variance. How do we calculate the variance? Although a measure of variability, the variance also qualifies as a type of mean, that is, as the balance point of some distribution. To qualify as a type of mean, the values of all scores must be added and then divided by the total number of scores. In the case of the variance, each original score is re-expressed as a distance or deviation from the mean by subtracting the mean. So, for each of the data point, we can measure its variability by subtracting the mean from that data point. For each of the three distributions in figure 4.1, the face values of the 7 original scores shown as numbers along the x-axis have been re-expressed as deviation scores from their mean of 10, as shown by the numbers in the boxes. Let's see. Here, all the boxes in distribution A is labeled as 0, which signifies that all the data points in distribution A have 0 variability from the mean. Whereas for distribution B, there are 5 scores or 5 data points which are labeled as 0, signifying that there are 5 data points which equal the mean. There is one data point which is labeled as -1, which means that it is 1 unit less than the mean, and there is one data point which is labeled as 1 positive, which signifies that it is 1 unit greater than the mean. For the distribution C, there are two scores which are labeled -1, which means there are two scores which are 1 unit less than the mean. There are two scores which are labeled 1, which signifies that there are two scores which are 1 unit greater than the mean. There is one score similarly which is labeled as -3, and there is one score which is labeled as +3, signifying that they lie 3 units apart from the mean, one towards the left of the mean, that is, one value is smaller than the mean, and the other towards the right of the mean, signifying that it is greater than the mean. For example, in distribution C, one score coincides with the mean of 10, 4 scores deviate 1 unit from the mean, and 2 scores deviate 3 units from the mean, yielding a set of 7 deviation scores. So in all the three distributions, we get 7 deviation scores corresponding to the 7 data points that we have. Now, mean of the deviations is not a useful measure. So what we can see is that in all the three distributions, if we add up the variability scores for each of the data points, it will ultimately come out to be 0. In distribution A, since all of the data points are labeled as 0, it comes out to be 0. In distribution B, there are 5 scores labeled as 0, and there is one which is labeled -1, one which is labeled +1. So the sum again comes out to be 0, and similar is the case for distribution number C. This happens because we are calculating the variance of a data point from the mean. Now, since the mean is by definition the center of the distribution, it the values of the individual data points, the variance values of individual data points cancel each other out. That is why mean deviation is not a useful measure of variance. That is what it says. The sum of all deviations from their mean always equals 0. In effect, the sum of all negative deviations always counterbalances the sum of all positive deviations, regardless of the amount of variability in the group. Now, to rectify that, we find out the mean of the squared deviations. Before calculating the variance, which is a type of a mean, negative signs must be eliminated from deviation scores. Squaring each deviation, that is, multiplying each deviation by itself, generates a set of squared deviation scores, all of which are positive. Now, when we square up the deviation scores, the negative signs will get removed, and what we will get back is a positive deviation value. Now it's merely a matter of adding the consistently positive values of all squared deviation scores and then dividing by the total number of scores to produce the mean of all squared deviation scores, also known as the variance. So when we sum up all the squared deviations and divide it by the number of observations, we get a metric which is known as variance. Now, variance also has some weaknesses. What is that? Since we have squared the deviation scores, we have also squared the units as a result. That is what it says. In case of the weights of 53 male students in table 1.1, it is useful to know that the mean for the distribution of weights equals 169.51 pounds. But it is confusing to know that because of the squared deviations, the variance for the same distribution equals 544.29 squared pounds. Now, this 544.29 squared pounds does not give much of an intuition, or much of a it is not that easily understandable. What you might reasonably ask are squared pounds. It is not that easily understandable. To get to a better metric of variance, we come to a metric known as standard deviation, which is a very important measure of variance or variability, which is used thoroughly in throughout statistics. To rid ourselves of these mind-boggling units of measurement, simply take the square root of the variance. This produces a new measure known as the standard deviation that describes variability in the original units of measurement. For example, the standard deviation for the distribution of weights equals the square root of 544.29 squared pounds, that is 223.33 pounds. So when we take the square root of the variance, we get back to the original units of measurement, and it gives us a much better or much more understandable metric. The standard deviation is the square root of the mean of all squared deviations from the mean, which is nothing but that the standard deviation is the square root of the variance. Now, how do we interpret a standard deviation? You might find it helpful to think of the standard deviation as a rough measure of the average amount by which scores deviate on either side of the mean. So, a standard deviation can be thought of as a rough measure or the average amount by which each of the scores deviate on either side of the mean. What it goes on to say is that majority of the scores are within one standard deviation. For most frequency distributions, a majority, often as many as 68% of all scores are within one standard deviation on either side of the mean. This comes from the normal distribution where 68% of all scores are within one standard deviation on either side of the mean. Essentially, the same pattern describes a wide variety of frequency distributions, including the two shown in figure 4.3. This is the figure 4.3 where it says that a majority of the scores lie within one standard deviation of the mean. Here, the mean is signified by x bar, and one positive deviation from the mean is signified by x plus 1s, x bar plus 1s, where s stands for standard deviation, and the one standard deviation below the mean is signified by x bar minus 1s. So, a large majority of the values in this distribution will lie between x bar or the mean minus 1 standard deviation and x bar plus 1 standard deviation or the mean plus 1 standard deviation. As suggested in the top panel of figure 4.3, if the distribution of IQ scores for a class of 4th graders has a mean of 105 and a standard deviation of 15, a majority of IQ scores will be within one standard deviation on either side of the mean. So, one standard deviation less than the mean would be 105 minus 15, that is 90. One standard deviation greater than the mean would be 105 plus 15, that is 120. So, a majority of IQ scores should be within one standard deviation, that is between 90 and 120. By the same token, as suggested in the bottom panel of figure 4.3, if the distribution of weekly study times for a group of college students estimated to the nearest hour has a mean of 27 hours and a standard deviation of 10 hours, a majority of their study times should be within one standard deviation on either side of the mean, that is 17 and 37 hours. So, in such a distribution also, which is not a perfectly normal distribution, it is a skewed distribution. Here also, a majority of the scores or observations would be within one standard deviation of the mean. That is, roughly 68% of the scores would be within one standard deviation of the mean. A small minority of scores deviate more than two standard deviations. The standard deviation can also be used in a generalization about the extremities or tails of frequency distributions. For most frequency distributions, a small minority, often as small as 5% of all scores, deviate more than two standard deviations on either side of the mean. If we come back to the figure, what we can see is that there is a very small minority of scores which are less than which are more than two standard deviations away from the mean. For most frequency distributions, a small minority, often as small as 5% of all scores, deviate more than two standard deviations on either side of the mean. This generalization describes each of the distributions. For instance, among the 7 deviations in distribution C, none deviates more than two standard deviations on either side of the mean. As suggested in figure 4.3, relatively few 4th graders have IQ scores that deviate more than two standard deviations on either side of the mean of 105, that is, IQ scores less than 75 or more than 135. These two generalizations about the majority and minority of scores are independent of the particular shape of the distribution. As we saw in these figures, these two distributions have very different shapes. Still, this generalization about the majority of the scores being within one standard deviation of the mean and a minority of the scores, that is less than 5% of the scores, being greater than two standard deviations away from the mean, hold for both these kinds of both the distributions, irrespective of their shape. In figure 4.3, they apply to both the balanced distribution of IQ scores and the positively skewed distribution of study times. In fact, the balanced distribution of IQ scores approximates an important theoretical distribution, the normal distribution. Standard deviation, a measure of distance. There is an important difference between the standard deviation and its indispensable co-measure, the mean. The mean is a measure of position, but the standard deviation is a measure of distance on either side of the mean of the distribution. Note that the mean x bar of 169.51 pounds has a particular position or location along the horizontal axis. So, the mean in a distribution has a particular position in an axis. So we can mark 169.51 pounds on the axis. It is located at that point and only at the point corresponding to 169.51 pounds. On the other hand, the standard deviation S of 23.33 pounds for the same distribution has no particular location along the horizontal axis. Using the standard deviation as a measure of distance on either side of the mean, we could describe one person's weight as two standard deviations above the mean by x bar plus 2s, another person's weight as two-thirds of one standard deviation below the mean by x bar minus two-thirds of s. So s signifies a distance. It Using it, we can identify the position of an observation in a distribution. So when we say that an observation is one standard deviation above the mean, what we mean by that is to arrive at the distribution, we can add one unit of standard deviation to the mean. And when we say that one observation is 2 units less than the mean, two standard deviations less than the mean, what it means is that to get to that point, we have to subtract two standard deviations from the mean. So that point can also be signified or also be identified as x bar minus 2s. The value of a standard deviation cannot be negative. Standard deviation distances always originate from the mean and are expressed as positive deviations above the mean or negative deviations below the mean. Note, however, that although the actual value of the standard deviation can be 0 or a positive number, it can never be a negative number because any negative deviation disappears when squared. So, although we specify a data point as being two standard deviations below the mean, or we identify it by saying x bar minus 2s, the standard deviation is not negative. It is the position of the point that is signified by x bar minus 2s. The deviation is always a positive quantity because to arrive at the standard deviation, we first calculated the variance. And while calculating the variance, we squared the deviation scores from the mean, which got rid of the negative signs. So, the standard deviation will never be negative. As with the mean, statisticians distinguish between population and a sample for both the variance and standard deviation depending on whether the data are viewed as a complete set, that is a population, or as a subset, that is a sample. So in statistics, we often distinguish whether we are working with a sample or a population. And we try to incorporate the differences between a population and a sample in our formulas that we work with. Calculating the standard deviation requires that we obtain first a value for the variance. However, calculating the variance requires in turn that we obtain the sum of squared deviation scores. The sum of squared deviation scores, or more simply the sum of squares, symbolized by SS, merits special attention because it's a major component in calculations for the variance as well as many other statistical measures. So, how do we specify the sum of squares for a population? It is the summation of all deviations from the mean, that is, summation of x minus mu squared. Here, to identify the mean, we have used the Greek letter mu. So, one thing to note is that while we are working with a population, we always use Greek letters to identify the population parameters. Now, what is the formula for standard deviation? Alright, we are first looking at what is the formula for sum of squares for a sample. So, for a sample, it is the same, that is, we subtract the sample mean from the individual observations and square them up and sum them all up. What is the standard deviation for a population? Since the variance is the mean of all squared deviation scores, it can be defined as the sum of all squared deviation scores divided by the number of scores. So, what is the variance? It is the sum of all squared deviation scores divided by the number of scores. So, variance, which is denoted by sigma squared, is equal to SS by n. Here, to denote the population parameter, we are using capital N and sigma, where the squared lowercase Greek letter sigma squared represents the population variance, SS is the sum of the squared deviations for the population, and n is the population size. To rid us of the bizarre squared units of measurement, take the square root of the variance to obtain the standard deviation. So to obtain standard deviation, what we do is we divide SS by n and take the positive square root. Now, the formula for variance of a sample is SS by n minus 1. So, one distinct difference that we can see in this formula from the formula for the population is that to calculate the sample variance, we are dividing the sum of squares by n minus 1 instead of n. And the standard deviation is the square root of the quantity, that is square root of SS upon n minus 1. Now, the question is, why are we using n minus 1 in the denominator? Using n minus 1 in the denominator solves a problem in inferential statistics associated with generalizations from samples to populations. In inferential statistics, what we are often doing is we are using the sample to understand or estimate a value or a parameter for the population. The adequacy of these generalizations usually depends on accurately estimating unknown variability in the population with known variability in the sample. In the first example that we worked out in this chapter, what we saw is that measuring the variability is very important if we are trying to infer something from the sample. The adequacy of these generalizations usually depends on accurately estimating unknown variability in the population with known variability in the sample. But if we were to use n rather than n minus 1 in the denominator of our estimates, they would tend to underestimate the variability in the population. This tendency would compromise any subsequent generalizations, such as whether observed mean differences are real or merely transitory. So, to understand whether the observed mean difference after an experiment is real or it is merely transitory, it is important for us to be able to calculate the population variance accurately. Now, to calculate the population variance accurately, we use n minus 1 in the formula instead of n. It will get clearer as we move along. Assume that the five scores 7, 3, 1, 0, and 4 in table 4.3 are a random sample from some population whose unknown variability is to be estimated with a sample variability. So what we have here, let's assume that we have a sample of 5 scores, that is 7, 3, 1, 0, and 4, which is a random sample from a population whose variability we are trying to estimate from the sample. If we take a look at the table 4.5, which shows us the 5 observations of, that is 7, 3, 1, 0, and 4, the first step to calculating variance is subtracting the the mean from the observation, each data point. So here, when we are subtracting each data point from the mean, what we get is 7 minus 3 is 4, 3 minus 3 is 0, 1 minus 3 is negative 2, 0 minus 3 is negative 3, and 4 minus 3 is 1. Although it might seem that there is no problem with estimating a variability like this, but one point to note here is that the sum of all the variabilities around the mean is always 0. So instead of these 5 variability scores, if we are given only 4, that is, if we are given 4, 0, negative 2, and negative 3, which sums out to be 4 minus 2 is 2, 2 minus 3 is negative 1. If we are given only these 4 values, and we can calculate the sum of these variabilities and find that it is coming out to be negative 1. We could then automatically infer that the fifth observation would be one variability or one unit of variability away from the mean, because ultimately the sum of all the 5 variabilities around the mean has to come to 0. So in essence, the last observation, or given any 4 observations, the remaining observation is not really free to vary around the mean. Let us say that uh, we have a scenario where we know the population mean, which generally is not the case, and the population mean is almost always different than the sample mean. So while calculating the variance, what we are trying to do is we are trying to measure how far each of the data points vary freely around the mean. Now, in this case, suppose we want to calculate the variability of the population based on the sample. Since we are getting the mean from within the sample, all the sum of the variabilities will always come out to be 0. So the fifth variation depends on the earlier 4 variations, because the sum of all the 5 variations is 0 around the mean. To understand why n-1 works, let's look more closely at deviation scores. The definition formula for the sample sum of squares specifies that each of the 5 original scores x be expressed as positive or negative deviations from their sample mean x bar of 3. At this point, a subtle mathematical restriction causes a complication. It's always true, as demonstrated on the left hand side of table 4.5, that the sum of all scores when expressed as deviations around their mean equals 0. Given values of any four of the five deviations, the value of the remaining deviation is not free to vary. Instead, its value is completely fixed because it must comply with the mathematical restriction that the sum of all deviations about their own mean equal 0. For instance, given the sum of the four top deviations on the left hand side, the value of the bottom deviation equals 1 as it does because of the zero sum restriction. Since this restriction applies to any four of the five deviations, given the sum of the bottom four deviations, the value of the top deviation must be equal 4. So, in case we have 5 observations and we are given any 4, we are able to measure the variability of the fifth score based on the sum of variabilities of the initial 4 scores. Now consider that the unlikely scenario that we know what a population mean is. In that case, the let's say uh, it is some other value than the sample, as it will always be. In our case, the sample mean was 3, and let's say the population mean is 2. So in this case, the fifth observation is also free to vary because the mean is not coming from within the sample. The mean is coming from the population. So all the 5 scores are free to vary around the mean. In this case, to find out the variance, we can divide the we can have 5 in the denominator as is shown here. For the sake of the present discussion, now assume that we know that the value of the population mean mu is equal to 2. Any value assigned to mu other than 3, the value of x bar would satisfy the current argument. It's reasonable to assume that the values of mu and x bar will differ because a random sample exactly replicates its population rarely, if at all. Furthermore, assume that we take a random sample of n is equal to 5 population deviation scores, that is x minus mu. Then these 5 known deviation scores will serve as the initial basis for estimating the unknown variability in the population. So we are using the 5 values from the sample to assume the or to measure the unknown variability in the population. The zero sum restriction applies only if the 5 deviations are expressed around their own mean, that is, the sample mean x bar of 3. It does not apply when the 5 deviations are expressed around some other mean, such as the population mean mu of 2 for the entire population. In this case, since all 5 deviations are free to vary, each provides valid information about the variability in the population. So, since each of the 5 values are free to vary, they will provide a definite value for the variability in the population. Therefore, when calculating the sample variance based on a random sample of 5 population deviation scores, it would be appropriate to divide this sample sum of scores by n of 5 shown in the right hand side of the table. Now, what happens when mu is unknown? It would be most efficient if, as above, we could use a random sample of n deviations expressed around the population mean to estimate variability in the population. But this is usually impossible because, in fact, the population mean is unknown. Therefore, we must substitute the known sample mean x bar for the unknown population mean mu, and we must use a random sample of n deviations expressed around their own sample mean x minus x bar to estimate variability in the population. Now, since most of the times we do not have the measure of the population mean, we contend with the sample mean. Now, since we are figuring out or we are picking out the mean from within the sample, what will happen is the nth observation will be dependent upon the previous n minus 1 observations. Only n minus 1 of the sample deviations supply valid information for estimating variability. One bit of valid information has been lost because of the zero sum restriction when the sample mean replaces the population mean, and that's why we divide the sum of squares for x minus x bar by n minus 1 and not n. This term is known as degrees of freedom. So, degrees of freedom refer to the number of values that are free to vary. The important term here is free to vary. In case where, in the case where we were uh, estimating the population parameter based on the sample parameter, what was happening is the mean was coming from within the sample. So, the fifth observation or the nth observation was always dependent upon n minus 1 observations because of the mathematical reason that the variability around the mean for any given set of observations is always 0. So, to satisfy this condition, the fifth observation or the fifth variability was always dependent upon the previous n minus 1 or 4 variabilities. The concept of degrees of freedom is introduced only because we are using scores in a sample to estimate some unknown characteristic of the population. So, this concept of degrees of freedom is used only when we are trying to infer something from a sample. If we are trying, if we don't have anything to infer from the sample, or if we are not trying to infer anything from the sample, we could have very well divided the total sum of squares by n. But since we want to infer something from the sample, since we want to find out a population metric from the sample, we have to estimate the variance properly. And to estimate the variance properly, we would have to consider only the number of scores which are free to vary. If the sample sum of squares were divided by n, it would tend to underestimate variability in the population. This would occur because there are only n minus 1 independent deviations in the sample sum of squares. A more accurate estimate is obtained when the denominator term reflects the total number of independent deviations, that is, the number of degrees of freedom. So, here the degrees of freedom is n minus 1. The degrees of freedom always indicate the number of values that are free to vary in a set of values used to estimate some unknown population characteristic. So, degrees of freedom will always indicate the number of values that are free to vary in a sample when we are trying to estimate some unknown population characteristic from the sample. Coming to another metric of variability is the interquartile range. The interquartile range is simply the range for the middle 50% of the scores. More specifically, the IQR equals the distance between the third quartile and the first quartile. Since most distributions are spread more widely in their extremities than their middle, the IQR tends to be less than half the size of the range. Now, the interquartile range has a key property. It is that it is resistant to the distorting effect of extreme scores or outliers. Because we are removing the top 25% and the bottom 25% of the observations, we are in effect getting rid of the extreme values or the outliers. Thus, if you are concerned about possible distortions caused by extreme scores or outliers, use the IQR as the measure of variability, along with the median as the measure of central tendency. So, now in summary, what we can say is that measures of variability reflect the amount by which the observations are dispersed or scattered in a distribution. These measures assume a key role in the analysis of research results. So, if we are to ascertain whether a particular experiment is giving us a statistically significant result depends on our being able to calculate the underlying variability in the population properly. I hope this would have been helpful. Thank you. See you in the next chapter.